Hello everyone, Mr. Minnick's my name, math is my game. I'm recording this lesson for anybody in YouTube land that wants to know about polynomials. Also for my Algebra 2 students who are out because they be illin'. We're looking at polynomials. And we're going to look at part 2, and this is be the final part of lesson 1. And just to kind of give you an overview of where we're going with this, today what we need to talk about is toilet paper. I don't know why public bathrooms put the worst toilet paper ever in the stalls. It's actually not toilet paper, I'm sorry. It's turning points. Turning points. Polynomials have them, and we'll explain and decode the myth of what they are and what they aren't. So we'll be talking about turning points, and we're going to be talking about something called finite order differences. Finite order differences. Both of these concepts at first sound really complicated, but they're not as bad as it seems. So that's basically it. There's just two big ideas that we need to look at today. Okay, shouldn't take too long. So suppose we had something like y equals x cubed. If you've never seen this function graphed, you can either take my word for it or we could look at Desmos, but when you graph it, it looks something like this, okay? Looks something like that. So the end behavior of it, to recap on yesterday, the end behavior of it, because this is positive, we know that it goes up on the right. Because this is odd, it's going to do the opposite thing on the other end. So the end behavior, we say, is down and up. So you're probably still asking yourself, what the heck is this turning point business? I just want to get to it so we can be done. So here's what a turning point is. A turning point is where the graph goes from either increasing to decreasing, or the other way around, or decreasing to increasing, or decreasing to increasing, or decreasing to increasing. So when we say decreasing and increasing, we're talking about the y values as the graph goes from left to right. From left to right, what's going on, what's happening to the values of y. So I need some kind of something to keep track of this. I'll use a star dancing in the night with a tail as big as a kite, So this star traveling along this graph from left to right, does it ever go from increasing to decreasing? It does not, right? It does not go from increasing to decreasing. So what we would say about this is there are no turning points. There are no turning points here, right? On this particular graph, there are no turning points because from left to right, that star dancing in the light with a tail as big as a kite is always increasing. Does that make sense? Okay. So what it's a good idea, what it's a great exercise to do is to look at the degree. Oh man, that was weird. To look at the degree and to look at the number of turning points. To look at the degree and to look at the number of turning points. Whoop, 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 whoop. And we'll see if we could draw a conclusion about this. I don't think the right side of the table needed to be that long. But let's think about a line for a minute. When we graph a line, so if the degree is 1, when we graph a line could do this. And here comes our star dancing in the light. Or is it dancing in the night? A star dancing in the... Is it dancing in the light or the night? Anyway. So does this have any... what is it? Night? Okay. Night makes more sense, yeah. So does this have any turning points? Okay. So there's none. There are 0 turning points in that case, right? Let's look at a parabola. Parabola, I should say. Let's look at a parabola. So we're looking to see if the graph goes from increasing to decreasing or decreasing to increasing. So here comes our star dancing in the night. And it's decreasing, 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 stops decreasing, increasing. So how many turning points are there? Turning point is where it goes from increasing to decreasing. So there's one turning point here. Okay, there's one turning point here. Now let's look at a third degree polynomial. Earlier we saw x cubed, and x cubed looks, oh gosh, dang it. X cubed just looked like this. And we said x cubed has no turning points. But there are some cubic functions that sometimes look like this. Let's see if we can follow this one. Increasing, 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 stops. Decreasing, 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 stops. Increasing, increasing. How many turning points does that have? 2. This is kind of unusual. This reminds me of Carlton Banks. It's so unusual to be loved by anyone. Do-do-do-do-do-do. It's so unusual to be loved by anyone. So let's look at a fourth degree polynomial and see what's going to happen here. Some fourth degree polynomials look like a parabola. How many turning points does that have? Just 1. But other fourth degree polynomials look like an M. How many turning points does that have? 3. Are we starting to see the forest for the trees? Is 5 going to be 2 or 4? That's an excellent question. That's a terrific question. A fifth degree polynomial could look, well, I'm using green here. A fifth degree polynomial could look like this. How many turning points does that have? None. A fifth degree polynomial could look like this. How many turning points does that one have? 2. Or a fifth degree polynomial could look like this. How many turning points does that have? So it could have 2 or 4 or none. Are we starting to see the forest for the trees now? Can we draw a conclusion? Let's see if we can write this up using mathematical terms. An nth degree polynomial has at most this many turning points. At most this many. It's kind of important that we use the language at most. First degree had none, second degree had 1. Remember, the degree is n. So if the degree is n, the highest number of turning points would be what? 1 less than n, right? 1 less than n we write in math as n minus 1. Okay. If we didn't use the word at most or the language at most, we would say an nth degree polynomial has n minus 1 turning points or fewer by blank, blank, blank. So let's see. When we have 2, it could have 2. If the degree is 2, it could have 1 turning point. If it's 3, it could have 1 less than 3, which is 2, or none. So in 4, we went with 1 less, which is 3, or 1. 5 was 4, 2, or 0. Does anybody know what's going to go in the blank, blank, blank? It's kind of weird. An nth degree polynomial has n minus 1 turning points or fewer by an even number, or fewer by an even number. So if we use the word at most, it's just n minus 1. If it's an nth degree polynomial has how many turning points? Well, it's n minus 1 or less than that by some even number. And it can't have a negative number of turning points. So what if n equals 17? If n equals 17, there could be there could be 16 or fewer than that by an even number. What's fewer than 16 by an even number? 14 or 12 or etc. all the way down to nothing, right? Get the idea? Good. So I really like open-ended questions. So let's see if we can use our brains a minute and think about this. Suppose a polynomial function has end behavior of up and has 3 turning points. What is its least degree? What is its least degree? In other words, what's the lowest power that thing could take? What's the lowest power that thing could take? So let's think about this. The end behavior's up, right? The fact that the end behavior's up should tell us something about the power. The power's got to be what? Odd or even? If it's doing the same thing on the ends from our end behavior study, it's going to have an even degree, right? So the degree is going to have to be some even number. And then we had that whole thing about the n-1 business. Well, if it has 3 turning points, what would the degree be? Let's see if we can work backwards from our table. If it had 3 turning points, what's the degree in that particular case? 4, right? And it's kind of important, they phrased it the least degree. So the answer to this one is 4, right? Yeah, question. Is 4 the only one that has 3 turning points? That's an excellent question. No. A 6-degree polynomial could do something like this. It could go up on the left and they could do whoop, 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 whoop. It could look like that, right? So there's 1, 2, 3, 4, 5 turning points. A 6-degree polynomial could also look like this. A 6-degree polynomial could also just have 3 turning points. Okay, but the question says, what's the least degree? See how that language makes it, narrows it down to just a 4? That makes sense? Okay. I know some of this stuff's kind of wild. So let's see if we can figure this out. What's the least degree of this polynomial? So we better count turning points. How many turning points are there? There's 1, there's 2, there's 3, there's 4. So what's the lowest degree polynomial this could be? 5. Does that make sense? Good. It could be a 7th degree, could be a 9th degree, but the least degree would be 5. Okay. Because of the end behavior, it couldn't be a 6th or an 8th or a 10th degree. Does that make sense? Would I have asked for the greatest degree? No, because of the infinite nature of cycling up by 2. Yeah, I wouldn't ask what the greatest degree is. Excellent question. Cool. So the last bit of information we need to talk about then today is these finite order differences. Finite order differences. The gist of what we're going to be doing here is we're going to be subtracting y values. That's kind of like the overview of what the essence of this is. We're just going to look at y values and subtract them. I got to be honest with you, my first 5 years of teaching Algebra 2, I skipped this because I didn't understand it. But I'm going to do my very best to explain it to you in a way that makes perfect sense of this. It says this. It says an nth degree polynomial, an nth degree polynomial, an nth degree polynomial function, an nth degree polynomial function has nth order finite differences. And I left something out of here. An nth degree polynomial function has constant nth order finite differences. That phrase is really weird. You're probably looking at that and saying, what'd you talk about, Willis? An nth degree polynomial function has constant nth order finite differences. Wow. What does that even mean? I'll show you what it means. The y value differences the first time. I'm going to clone this. The y value differences the second time. And I'm going to clone this. The y value differences the third time. So the y value differences, if they're not the same here, but they are the same here, then what that means is that the degree is 2. It's kind of confusing. An example is going to make great sense of this. But basically, you're going to subtract the y values if you get different differences the first time. The polynomial is not linear. If you subtract the y values again, and you get different differences for the y values, then it's not quadratic. If you have to do it a third time and they're not the same, then you have to go a fourth time, and eventually they're going to be the same differences. And however many times it takes, that's what the degree of the thing is. That's what the degree is. So however many times you have to subtract, that's going to give you the degree of the thing. So, like I said, an example, I hope, will clear this up. And the big thing is just being consistent with subtracting. That's the big thing, just being consistent with the subtracting. So I've got a polynomial. I'm not going to tell you the degree. But here it is, example. Here's my table, x and y. So I'm going to go 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6. And I got to put my y values in. They're 1 and -2. -9, -14, -11, 6, 43, and I'll go up to 7, and 7, 106. So what some people do is they try to see, okay, so it was decreasing, and then it starts increasing again. So there's one turning point, so it's quadratic. Well, you don't have the whole picture. There's not enough information to tell, and you might guess wrong. Some people like to guess. I'm going to call this my FOD, my first order differences. My first order differences. The key to this is subtracting consistently, subtracting in the same order. So, and it's kind of weird what happens in the table too. It's kind of weird what ends up happening in the table. I probably shouldn't have extended that over. That's my bad. I should neck myself for that. I will. There we go. I don't know if you heard that. So when I find the differences, I'm finding the differences in the y values. I'm finding the difference between 1 and -2. So what's 1 minus minus 2? 1 minus minus 2. It's going to be 3, right? Everybody see what I did there? You got to be consistent. Notice how I took the top number and subtracted the bottom number from it? So when I go again, I got to be consistent. So the next time, I'm going to take negative 2 minus minus 9. Negative 2 minus minus 9. So what's negative 2 minus minus 9 going to be? Well, it's going to be negative 2 plus 9. It's going to be 7. Going to be 7. Now, are 3 and 7 the same? Are 3 and 7 the same? No. So that tells me right off the bat, this is not linear, which I kind of knew already, but this is not linear. Okay, so I got to keep going. I got to go because I don't know how far out I'm going to have to subtract. So then we got negative 9 minus minus 14. So is that going to be 5? Okay. So then I got to take negative 14 minus minus 11. So what's that going to be? Is that negative 3? Negative 3, okay. And then I got negative 11 minus 6. So is that negative 17? And then I got 6 minus 43. 6 minus 43, so that's negative, is that 30? Negative 37, okay, thank you. Negative 37. And then lastly, but not leastly, 43 minus 106. That's 57 and another 6. Is that 63? Yeah, it's 63 and it's negative, right? Okay. So that's what happened when I found my first order differences. And I see that they're not the same, so the function's not linear. So let me try finding my second order differences. So again, I'm subtracting these y values. This time I'm going to take 3 minus 7. What's 3 minus 7? Negative 4. Remember, be consistent with how you subtract. Be consistent with how you subtract. I took the top number minus the bottom number, so now I'm going to take 7 minus 5. 7 minus 5 is going to be, is that 2? Are negative 4 and 2 the same? No. So this is not quadratic either. I thought it might be quadratic, but it's not. So now I'm going to take 5 minus minus 3. 5 minus minus 3, what's that going to be? 8, good. So then I'm going to take negative 3 minus minus 17. Negative 3 minus minus 17. Is that 14? Okay. And then negative 17 minus minus 37. It's going to be 20. And then negative 37 minus minus 63. So that's 3 and another 23. That's 26? 26. Okay. All right. So my second order finite differences were not constant. So that didn't work. So I got to go until they're the same. When I say constant, I mean they're going to end up being the same. So my third order finite differences. So this was first, this was second, and I'm about to find the third. So what's negative 4? Dang it. What's negative 4 minus minus 2? Shoot. Negative 6. Okay. So negative. My smart board's cooperating greatly here. Negative 4 minus 2 is negative 6. What's 2 minus 8? Negative 6. Oh, this is awesome. What's 8 minus 14? Negative 6. What's 14 minus 20? Negative 6. And 20 minus 26? Those are all constant, aren't they? So what's that mean? It means we found the degree. So the answer is that our degree then is what? Our degree is how many times it takes to get that. So the answer is that the degree is 3 because it took us 3 times of subtracting to get that. Does that make sense? I hope that one example suffices to get it. The big thing is just be consistent when you subtract. I want to show you real quick with a linear. It shouldn't take long with a linear. Just to kind of confirm. Yeah, if the degree's high, it takes a long time for sure. So suppose we had this for our x and a y. 1, 2, 3, 4. 1, 2, 3, 4. And then 2, 3, 4. 2, 3, 4, 5. So our first differences are going to be -1, -1, -1. Oh, look at that! Right off the bat, right? So that means this one's linear. That makes sense? Good. It's been real. It's been fun. I'd like to give a shout out to the future Mr. Minnick. Shout out to the second period class. Shout out to the sophomores. If you're watching this back, have a great day. See you. Good.